So now, if we have the ligand attached, the gate opens, sodium rushes in, that changes my membrane potential. So now the next gated protein. So this one was my ligand gated, okay? Locate it close to it, because remember, I have now changed the inside of the cell to positive. So now, located next to it is voltage gated, meaning it's got a gate, okay? So now, if the sodium's rushed in, I've changed my potential. Does that mean I affected the voltage of my cell? Yes. So if I affected the voltage of my cell, the next one, a protein that will get affected from that is my voltage gated. Because now my voltage gated is going, well, now wait a minute, a bunch of positives just came in, so, oh, good deal. This gate gets to open. So now my voltage gated opens. Once again, outside the cell is a lot of sodiums. So now what do you think is going to happen across the voltage gated that is a perfect fit for sodium? We're going to have more sodiums come in. So now I'm adding to the positiveness of my cell. The cell is going, hold up. This is enough. Because when this happens, the cell has to do something. And it can only withstand this for a certain amount of time. And the cell wants to go back to being more negative on the inside. So it says, wait a minute, we have to balance this out. I can't have this more positive on the inside than negative on the inside, okay? So we're going to find another protein, because when we see that we have our leak channels, ones that are just letting materials just go back and forth, something that they are very permeable to is potassium, which is also positive. When that cell's membrane potential is not affected, these potassiums help keep it balanced. But now I got those positives. I had my ligand gated channel open, and that let a bunch of sodiums in, which continued to make it positive, which affected my voltage gated, which made it more positive. So on this inside of the cell, I'm getting more and more and more and more positive. Okay? So, hold on. So now, the cell goes, stop. We need to balance. And we have to now use energy.
Clarifying question, the voltage and ligand gated channels affect membrane permeability?
Yes.
Okay.
Both of these are going to make the inside of the cell more positive. So the ligand-gated, voltage-gated. And it now says, stop. We need to go back to the natural state. So we have embedded in the plasma membrane what we call the protein. We call it the sodium-potassium pump. The sodium-potassium pump, that particular protein, remember, inside the cell, mitochondria are producing ATP. ATP is present. It can go and give some energy to the sodium-potassium pump. So the sodium-potassium pump, all right, the sodium-potassium pump, it will now push 3 sodiums out and let 2 potassiums in. Sounds weird because it's still positive, positive. But because potassium will get to just simply flow back and forth across one of those leak proteins, it's not really worried about it. But to push the sodiums out, potassium's got to cross. And my cell goes back to being negative on the inside. Patrick?
Is that an example of active transport versus the channel proteins of passive transport? Or is it something else?
That's going to be something else. Hold on to that thought, though, okay? Because let's take what we have just learned and put it into something we understand, okay? All right. The 2 cells of the body that are extremely dependent on this, okay? Nerve, muscle, all right? So let's take what we have just learned about this movement of these ions and creating a potential and put it together. So, think about moving your arm to write notes, all right? To do that, I need stimulus from a nerve. And I need that to go to a muscle cell. Okay, is everybody following me? So I'm going to need that nerve to meet a muscle cell. And I wish I was a better artist, okay, but I'm not. At the point where the nerve meets the muscle, I have a synapse. The nerve releases its product. Guess what that product serves as? a ligand. Okay? So, the product from the nerve serves as the ligand. So now, at the point of the synapse on the muscle cell, I have tons of ligand-gated proteins. So, in the membrane of that muscle cell, okay, I have tons. They are only found at the point where the nerve meets the muscle. But I still have the rest of that cell. So if at the point of where the nerve meets the muscle, and I have tons of the ligand-gated, and if what the nerve releases is a ligand, okay, that means all of them, we won't say all, but we have a lot that the ligand can attach to, those gates open, and sodium gets to rush in. Now, this is happening at a point of the long muscle cell. Is everybody with me? To get that muscle to contract throughout the rest, of that membrane of that muscle, what kind of gated protein do you think I'm going to find? Voltage. So now I'm going to find throughout the rest of this muscle membrane my voltage gated. It's negative on the inside, but because ligands opened and let sodiums in, I now created positive. All right? This voltage gate opens. I make it more positive. The next voltage gate it opens. I make it more positive. Do you see where I'm going with this? So, from the point of that synapse down the entire muscle cell, voltage gated are opening. And I'm changing the positive on the inside of my cell until I get the muscle contraction and things go, okay, we're done. And now I get to encounter my sodium, potassium pumps. I get to encounter sodium, potassium pumps. Sodiums get to go back out, cell gets to go back to negative, muscle gets to relax. The same thing is occurring on the membrane of the nerve. Gates are opening, sodiums are rushing in, and it'll have to go back to rest.
It's a constant cycle.
Pretty much. Now, Patrick?
Is that the same as the ATP power transport?
Yes.
Like that slide? So if it was a test, will we see sodium potassium pump or will we see ATP power transport?
But they're referred to both ways.
Okay.
Because for that sodium potassium pump to work, you've got to have the ATP power. Now,